carotenoids are controlling the reflectance behavior of plants. For 0.7 to 1.3 near infrared band is there, because for most of the plant 0.4 to 7 all plants will look green. So how do we know that this is X plant, this is Y plant? So it is the NIR band where the cell structure is controlling the reflectance pattern. So near infrared band is most important when you want to identify your differentiate crops. For this sphere band 1.3 to 3, here the water content of the leaves is controlling the reflectance behavior. I will show you in the next slide when there is healthy leaf there. You will get maximum reflectance is green and blue and red light is absorbed. For sick leaf, you will see, here in healthy leaf again, you will get highest reflectance in NIR here. But for sick leaf or dead leaf, you see the reflectance is almost here in dead leaf almost same. Sick leaf, though there is difference between, you can find the difference between visible, but you will not be able to discriminate the difference between healthy and sick leaf in the NIR band. That's why NIR band is more important for identifying the crops. Like this one, because if I have a plant, 3 plant types, one is healthy, another is stressed, and third one is severely stressed. You talk this one 0.4 to 0.7. I told you 0.4 to 0.5 blue, 0.5 to 0.6 green, 0.6 to 0.7 red. Here in 3 types of plant, almost you can see reflectance is, though there are differences, but almost it is similar. 0.7 to 1.3, there is NIR band there. Here you can see major differences. Here you can see healthy plant is showing you more reflectance. Stressed vegetation, reflectance is lesser than the healthy one. And severely stressed, lesser than the healthy and stressed. In this one, short wave region, where I told you that here the water content is controlling the reflectance behavior. Here we know that in green, in healthy plant, this green color is this one, water content is more. Therefore, absorption of radiations are more. That's why reflectance is less. But for stress vegetation, water content is less. And that's why reflectance is more and absorption is less there. That's why hope you are able to understand the reflectance spectrum of this healthy, disease and stress plants. Now, first I will be talking about crop monitoring. How we can do crop monitor through remote sensing. For this one, we need parameters like soil, crop, microclimate data, and drainage conditions. First, with remote sensing, how we can identify crop variability. In last few lectures, probably you now got that remote sensing is not completed with ground truthing. If you don't have any information about an area, You go to field and then you get the information about an area and you take GPS with you. Here you can see there is little crop growth there. Here crop growth is higher. So you will record the GPS location here, GPS location, all these points here, and then you plot this data on the satellite imagery, and then you see the spectral behavior. And then you, based on various indices like NDVI and others, you are able to differentiate crop variability on a landscape. So how we can do that? This was one of the aspect. If suppose I want to use optical data or microwave data, probably you know that many satellite data are now freely available, like Landsat, Sentinel, etc. And you know that Landsat 5, 7, 8 are optical data, and Sentinel-2 is also optical, but Sentinel-1 is microwave. And what we did was, here in Punjab, I will be showing you most of the studies in Punjab and India. So what we wanted to do here in July, because you know that in paddy or rice, you know, it is farmers use different dates for sowing. So what we did was we used Sentinel-1 data, Sentinel-2 data, and list4. Sentinel, Sentinel, sorry. Sentinel-1, Sentinel-1, that is microwave data. Sentinel-2 is optical data. List4 is your optical data. Then we were able to identify, here you can see all these squares here. All these are farm boundaries there. So we were in these regions, green color, you can see farmers have sown paddy between 9th and 20th June. Here, this is light pink color there. Farmers have sown paddy between 21st June to 2nd July. Yellow, this is 3rd to 14th. And this one is purple color, 15th and 27th July. So what we did was, for extracting paddy of different days from Sentinel-1, we developed a machine learning model, and then we applied that is, you know, decision tree thing, and we, based on our backscatter values, we developed a model, and then we implemented that model in MATLAB, and then we were able to identify, you know, paddy in different dates. Because once it was extracted, then we used Sentinel-2 and list4 data to verify if what we have extracted from Sentinel-1 and it was matching with that or not. So we got the accuracy around 85 to 90% with this one. Then we wanted to know, where we have extracted paddy, how much is the probability there because we are going for field level information. How much probability is there our classification based on decision tree is correct or not? So you can see here with green color, there was probability more than 65% was there, where we were able to identify paddy correctly. With this one yellow color, probability was medium, and this one here, red color probability was lesser than 35%. And this study was with limited ground truth only. Now, with cropping system, because Space Application Center, they did a study on how cropping system of Punjab can be extracted using remote sensing and satellite data. So Space Application Center and Punjab Remote Sensing Center, they used advanced wide field sensor data that was acquired from October 2004 to May 2005. Radar set data they used, then they used 10-day composite NDVI to see how the cropping system. So, and ultimately SAC and PRSC found that here in this northern part where the rice wheat is the major cropping system there, and here in the southern part cotton wheat is there, and cropping intensity was around 204%. And this was the one application. And now what is the application? Because people are talking about now precision farming. So what happened with that? Because we survey that area, or if you don't want to survey, then what you do is you use a satellite imagery, but then you built in some algorithms for that. And what then, based on algorithm, you set this much of fertilizer will be applied based on these spectral indices value. So suppose for this area, you can see here the crop growth is, or the field is having some variable information than this part. So with automatic control of sprayers and fertilizers, here the application of fertilizer will be varied than this one. So that's why remote sensing is important to save our resources here, because you can use either high resolution satellite imagery, or you can use proximal sensors. Proximal sensor like spectroradiometer you can use. So this is the thing, this is the one of the application of proximal sensing and remote sensing in variable rate application of fertilizers and pesticides. Another thing we did was, here we want to identify disease with remote sensing. So what we did was, here in potato there is one disease, late blight is there. We wanted to identify, this is one northeastern part of Punjab where that is one of the major potato growing area is there. Here you can see yellow region there. This is area under potato. So then in October-November 2018, we use Sentinel-2 optical data, which have 13 bands there. And based on the spectral indices, here we were able to identify which is the disease potato and which is the healthy potato. So based on that, because now if we are able to identify which is the disease, which is the healthy, then government can take action for the monitoring of disease. Otherwise, because if we know the point scale data, it seems impossible. And for this one, we got the continuous data. Now, this was about optical data and microwave data, where I showed you how this microwave data can be used for crop identification of sowing at different dates, And then I showed you how variable fertilizer application can be seen, and with this optical data how we can identify different diseases. Now come to hyperspectral data. This was, I showed you all these about the optical or microwave images. Now I'm talking about hyperspectral data. What is difference between this multispectral and hyperspectral data is that because multispectral data doesn't have any continuous bands, but with hyperspectral data you get hundreds of bands, but these are continuous data. Like this one, I was telling you this optical data 0.4 to 0. So suppose blue band is there 0.45 to I say 0.47 micrometer also. So, but then you are losing information from 0.41 to 0.449 or 0.471 to 0.500. But with hyperspectral data, you get the continuous information. Like again in my multispectral, suppose bandwidth is 0.445 to 0.46. The central bandwidth is 0.455. And but then you are losing some information. If I want to know 0.45, 0.46, 0.47, 0. Then hyperspectral data is more useful. With the hyperspectral data, you can see this is the again spectral profile of vegetation here. Here you can see here, this is, I told you this is your visible band. This is red edge band here. With multispectral, you can find this red edge band in Sentinel-2. And this is your NIR band there. This is your sphere band there. Here you can see here spectra. You can't see spectra here because their water absorption bands are there which have been removed. Here I told you 0.4 to 0.7 again chlorophyll, carotenoids and anthocyanin along with other factors control the reflectance spectrum. And with this 0.7 to 1.3, it is the leaf area index, crop biomass and plant density define the reflectance. Here lignin, cellulose, etc. determine the reflectance. What we did was here, we wanted to study the effect of nutrient stress on mange. So what we did was we did a field experiment and then where we grew mange. And there were 5 treatments there, 100% NPK, 75, 50%, 100% NP, 100% NP. 100% NPK means amount of nitrogen, phosphorus and potassium was applied that is recommended by agricultural university. That is 100% NPK. 75% NPK was where 25% lesser than the recommended dose of fertilizer. 50% NPK, 50% lesser than the recommended dose. 100% NP means where you didn't apply any potassium, only nitrogen and phosphorus were applied. 100% N means where phosphorus and potassium were not applied but nitrogen was applied. In 0.4 to 0.7 or 400 to 700 nanometer, you can see the highest reflectance was with 100% N. where there was only vegetative growth were there and plants were not supplied phosphorus and potassium. With 50% NPK, the highest was with 100% N. It was followed by 50% NPK. And it was followed by 75% NPK. And the lowest reflectance in this visible region was with 100% NPK. With this one, 0.7 to 1.3, this region there, trend become reverse now. Here the lowest reflectance we got the with 100% NP and the highest with 100% NPK or 100% NP. The thing is that if where we measure the potassium content of soil and the potassium content was sufficient enough to supply potassium to plants. Therefore, we were not able to differentiate between 100% NPK and 100% NP. In the sphere band, we got the highest reflectance with 100% N and lowest with 100% NPK. So this, if we have this type of understanding of the spectra, then we can relate with our nutrient or any other stress. Another thing, the other thing was, because in the previous slide I showed you here where the nutrient stress was there. Here we impose the moisture stress there, where we IW1, IW0.75, IW0.5. IW1 means we applied that amount of water that was recommended by the agricultural university. IW0.75 means 25% lesser amount. 0.5, 50% lesser amount. Again, we got the spectra like that with stress thing highest reflectance in the visible and with recommended lowest. In NIR region, reverse become the trend reversed. Highest with reflectance, highest reflectance in 100% NPK and lowest with 100% NPK and IW0.5. Here sphere band, I told you IW1 got more water, means lesser reflectance. IW0.5 got lesser reflectance, sphere region, more reflectance. Then we wanted to identify which wavelengths are optimum, which can potentially be used to identify the nutrient on water stress. Here you can see all these with this red points are blinking here. So these wavelengths are important to identify the nutrient or water stress. Now, this was the hyperspectral data. Now come to the point of thermal remote sensing, because now thermal remote sensing is gaining much more importance in agriculture, because people are now realizing the importance of water. You know, this thermal remote sensing, this Khanal et al. In 2027, they studied the thermal pattern in a field. Here you can see here the temperature was higher, here temperature was lower, and projections are there. There are few projections with increase in temperature, yield may decrease in future. So here you can see here where temperature was lower, here yield was comparatively higher, and where the temperature was higher, yield was comparatively lower. Now, you probably know that crop residue burning, you heard a lot in use in since last few years. Punjab, Haryana, and in parts of UP, there is much crop residue burning there. So what we did was we used VIRS data and MODIS data where the crop residue burning was there, where the continuous crop residue burning was there. So in this field from 2015 to 20, where the crop residue burning was continuously there, or in these area crop residue, there was no crop residue burning. So then we related this one with the satellite derived moisture during these crop cycle period, and we found that where the crop residue burning was there, moisture content was lower, and where the crop residue burning was not there, moisture content during the crop cycle was higher. So that because it has big implications on water budgeting, because where the farmers have burnt crop residues, because soil moisture profile got depleted and they have to apply more water, either because if they are applying through irrigation they are using more water. So it has big implications on water budgeting. Now, what we are doing is, in addition to this crop monitoring and analytic things, we are the big implications of remote sensing and GIS is in estimation of crop yield. So, one paper by Dwivedi et al. From Mahalabonis Crop Forecasting Center, they have published a good paper on this one, estimation of crop yield using satellite remote sensing, and we are using the similar methodology. So what we are trying to do is we are using NDVI product of MODIS, inset data, photosynthetic active radiation from MODIS, reflect from Sentinel-2, NDVI and LSWI from derived from Sentinel-2. This climate data, radiation use efficiency data, and then we are putting that one in there. We are integrating all these, and then we are trying to use this semi-physical approach to estimate crop yield. And we did a study with for wheat yield in Ludhiana district of Punjab using this approach. Then we found that there was a bias of 0.53 ton per hectare and RMSC was 0.61 ton per hectare. But we are still refining this methodology, but it shows that this remote sensing data along with climate and other parameters can potentially be used to predict the crop yield. Now, this was all about crop pattern, because I was showing you how crop growth monitoring can be done by remote sensing, how crop yield can be simulated, how this hyperspectral data can be used for identifying stresses. And besides that, soil is one of the important component of agriculture, and there are several factors which affect soil reflectance. Moisture content of soil, you know that. Soil texture, whether relative proportion of sand, silt, and clay content is there. How much iron oxide is there? How much organic matter is there? So, you know that there are in USDA, United States Department of Agriculture, according to them, there are 12 texture classes are there. And with this one, and then we can use hyperspectral data or multispectral data mounted through remote and proximal sensing for predicting soil properties. We did one study with hyperspectral data, and then we predicted clay content of soil. What we did was, actually, there was an area in Gujarat, Surendranagar, where we took soil samples and we used the average hyperspectral data. Corresponding to sampling sites, we extracted the surface reflectance of average data. Then we use various machine learning approaches to predict the clay content of soil. Among ANN, this partial least square regression analysis and others, we found that partial least square regression is more important, is better than other machine learning approaches to predict the clay content of soils. Now, then we know that because this was the prediction, but now people are talking about precision farming. On a landscape scale, you know that soil properties differ. And for this one, for identification of soil properties, how differ on a landscape, we need to study the spatial variability. And for spatial variability, geostatistics is more important. You know that with this all this distance, this is typical semi-variogram, where up to this distance there is some spatial relation, and after that there is no relation. And this distance is called, up to where there is a spatial correlation is there, it is called range. And up to this effect is called nugget effect. This nugget effect may be due to sampling error or analytic error. This is inherent thing which we can't avoid. And this is called, all this is called fill. So we, on a farm scale, we were able to identify the spatial pattern of organic carbon. Here you can see there was a landscape where it was slopy. Higher, this was the upper slope and this was the lower slope. Here we were able to identify where organic carbon was. This was a highly forested region was there, and organic carbon was varying between 3.25 to 4.76%. So here you can easily identify where organic carbon is higher there and organic carbon is lower there. Here. That's why, because where organic carbon and other nutrients are higher on a field or landscape, you can't give a generalized recommendation that has big impact on fertilizer application. Again, I told you this one with Surendranagar, Gujarat. If I see this wavelength there, where I showed you here the organic carbon lower, 0.12%, 0.36%, 0.76%. Here you can see the higher reflectance, medium and lower reflectance there. And these are the most important wavelengths which we derived through partial least square regression, which are helpful in identifying the organic carbon factor of organic carbon content of soil. Now, we studied crop, soil, etc. Now, people are talking about which areas are suitable for growing crops. So I will show you an example where we can see which area are suitable for growing crops. So what we did was, we took soil data, soil texture, drainage, macronutrient and micronutrient status of soil. Macronutrient means the nutrient which are required by plants in larger amount. Micronutrient status, the nutrients which are required by plants in smaller amount. Then we did mapping of macro and micronutrient through geostatistics. Then for the soil, these parameters were there. For water, we took groundwater quality for irrigation, depth to water level. Climate data, we took temperature and rainfall. For topographic data, we took slope. So, and then from the soil, all these four parameters, we prepared the soil suitability map. With this groundwater quality and depth to water level, we prepared irrigation suitability. Temperature, rainfall, we prepared climate suitability map. With this one, we prepared the slope suitability map. And then by taking into account all these parameters, we prepared maize suitability, paddy suitability, and wheat suitability map that is helpful in, suggesting alternative crops. This is the soil texture map of Ludhiana. Here you can see where the sandy loam soil is there. And where you can see here the loam and silt loam soil is there. Here this is the drainage pattern. This is a multi-macronutrient where you can see organic carbon, phosphorus and potassium status of soil. Multi-micronutrient, zinc, copper, iron, manganese there. We prepared these two maps through geostatistics. This is the depth to water level from June 2010 to 16. Here you can see water level is going down. It is average between 15 to 31 meter. It is around 3 to 8 meter. Here 8 to 15 meter. This is a groundwater quality for irrigation map. This is good water quality map. This is slight to moderate, and these are not good quality water map there. This is the rainfall map. This is a temperature map there. This is slope map there. Again, these were integrated in GIS. I already told you. Then we found that this area is suitable for growing wheat crop. This one, highly suitable area. This is moderately suitable. This is not suitable area of growing wheat in Ludhiana. This one here, this one is paddy. Here you can see by integrating all these factors, we found that 37% area of Ludhiana is suitable for growing paddy. This is moderately suitable and this is not suitable. And for this is for maize, we did similar thing. And then we integrated all these parameters where we found that the area which were marginally suitable or not suitable for paddy, because paddy is a water guzzling crop. And if we substitute paddy with maize, then we were able to save 450 million cubic meter of water. That has very big implications on crop diversification. So this is one of the potential of remote sensing and GIS for governance. And then because I told you that soil for this agriculture, soil moisture has also big implications, because soil moisture is quite important. So for soil moisture, people can use multispectral data for finding out the soil moisture. But mainly microwave data is used to determine soil moisture. So here, this is the Landsat A, a false color composite of Landsat 8. Here you can see soil moisture here, this one. Then we use two indices: normalized difference in water index, modified normalized difference in water index. NDWI is green minus nil divided by green plus nil, and MNDWI is green minus FIR and green plus FIR. When we use NDWI image, then we overestimated the soil moisture, because here these were mixed with built-up features. But when we use the MNDWI image, where we use green and sphere band, then built-up area were extracted from the moisture area. So it is more accurate. MNDWI is more accurate than NDWI image for extracting water features. Now, if we use microwave data for extracting soil moisture, you know that there are though there are many bands are there, X band, C band, S band, L band is there, but here you C band, it can go up to this one 6 centimeters or so. So now what we did was we are using Sentinel-1 data. Hello, could you please turn off your speaker, please? One of the participant, please. One of the participant, please. Could you please turn off your speaker? Organizer, could you please ask someone who has turned on their speaker? Please. Please, could you please turn off your speaker? We use Sentinel-1 data, and then we did the survey of an area and we measured soil moisture, and then we plotted a sampling site of soil moisture. We extracted backscatter value from Sentinel-1 that were corresponding to soil sampling moisture site, and then we found this relationship only, the relationship between measured soil moisture and backscatter value extracted from Sentinel-1. Sorry. Now, these are the operational soil moisture products that are derived using remote sensing. These are AMSR, E2, MIRAS, SMAP, Sentinel-1 data. So what we did was here, because Sentinel-1 SMAP, that is, soil moisture freely product is available at 1 kilometer by 1 kilometer resolution. So I mentioned that now because we did measurement of soil moisture from an area, and then these were the soil moisture sampling site were there, and these are 1 kilometer by 1 kilometer grid from SMAP Sentinel-1 there. And then we extracted from one, there are so many grids were there, and we extracted soil moisture from these grids, and we plotted thus with measured soil moisture against that was predicted extracted from Sentinel-1 and SMAP, and we found a correlation of coefficient of determination of 71%. So this is but Space Application Center is making available soil wetness index on the Mosaic website. You can see the moisture product of all India during this January 2020. So this was all about of application of remote sensing in agriculture and soil moisture. So I conclude that geospatial technology has the power to improve management and decision making by providing an execute snapshot of the reality on the ground. Analysis of satellite data from crops along with the information on other natural resources in GIS environment provide valuable information towards sustainable agriculture. The use of geospatial technology has significant potential for maximizing the efficiency of fertilizer applications. Spatial dependence should not be overlooked on future studies which explore the effect of management practices on crop production. Multispectral and hyperspectral remote sensing can be used for detection of abiotic and biotic stresses in crops. Research is required for using the microwave data for studying the spatial temporal variation in soil moisture at finer scale, because I was telling you at 1 kilometer by 1 kilometer product. User-friendly applications need to be developed for using the hyperspectral remote sensing data so that we can establish quantitative relationship between spectral reflectance and soil properties. Remote sensing has the potential to identify spatial variations in crop water status. Continuous improvement in satellite technology in terms of providing improved spatial and spectral resolution and revisit period. I'm aiming too high. That will greatly enhance the capabilities of mapping and monitoring of crops aiming towards sustainable agriculture. Thank you very much. Hello, ma'am.
Sir. Hello, sir.
Ma'am, I finished. Hope it was not too early.
Yes, sir. Actually, it is up to 11, sir.
Pardon?
Session from 9 to 11, sir. 2 hours session, sir.
Okay. Then I can give more. If we will give break for 10 minutes and then I will start another lecture. I can do that.
Okay, sir.
And if participants want to interact with me for
sir,
this much, after 5 minutes or so, we can start interacting and then I will give another lecture on that.
Okay, sir. So they have posted some queries here, sir, already.
Yeah. Sure.
Shall I, sir? Sir, one question is, where do we get particular crop suitability criteria for such kind of analysis?
Hang on, ma'am. I will be and then, yeah, sure, ma'am. Hang on, ma'am. Okay, where do we get particular crops that have such kind of and how? Okay, sir, because where do we get particular crops that have? Yes, sir, there is literature on that, where you can find the because for different states or even for different districts, it is this crop suitability criteria is there. So it is difficult because then you can use either ICAR, Indian Council of Agriculture Research website, or contact the agricultural university of your state to find the suitability of criteria, like for any sorghum crop. So say if which type of soil is suitable, which type, how much rainfall is required, and how much slope is required. So you need to identify all these. You need to take information from agricultural university, and then you integrate this data in GIS, and then you start doing your analysis. Hope you understood what I am trying to say? Yes. Another thing I can see, how do we quantify soil moisture through an MNDWI? The the initial answer for this one is that, because for if you want to measure soil moisture of an area, okay, and quantify that, so you need to go to field on the day of satellite pass. You need to measure soil moisture either using gravimetric method or volumetric method, and then you need to record latitude and longitude of your sampling sites. Come back, or then you analyze your satellite imagery, extract the MNDWI corresponding to your sampling sites, and try to develop a relationship between MNDWI and measured soil moisture. If if you get a good relation, means that's fine. Otherwise, you need to look for another options like microwave Sentinel-1 data or LOS pulsar data. That is, you need to identify. Sir, using which tools these results are found? Using tools, which results? These results. Are you talking about crop suitability thing? For this one, these results for, okay, if I assume that you are talking about crop suitability criteria, you need to use GIS. For interpolation, you can use geostatistics or kriging or inverse distance weight. Or for another things, you need to use another parameter, another tools. And when you want to do that one, when to integrate all these parameters, then you can use weighted overlay analysis. Which geostatistical algorithm have you used for raster survey? Sir, for soil characteristics, I use ordinary kriging for this one. Could you please provide practical exposure for soil data analysis? Happy to do, but you can contact me via email and I'm happy to assist you. Sure. Could we able to study subsurface soil? Sir, it is because, with subsurface characteristics, because even it is bit difficult to find the relationship between surface soil characteristics and reflectance. So it is bit difficult to do, but no, subsurface, it seems difficult. Yeah. So after 10 is there, 10:15 we will start another lecture for this agriculture thing.
Okay, sir.
Yeah, because I'm not used to give lectures like for continuously 2 hours. Did you carried out LCC? LCC means I couldn't get you. LCC, LULC or LCC? I didn't get you. I couldn't get you, sir. LCC? A land capability class. Yes, sir. That is one thing. Yes, we can do that. Yes, land capability class is easy to do, sir. When you have information about soil texture and other things. Yes, it can be done. Yes. Yes, sir. Mhm. Should we start? Hello?
Yes, yes, sure, sir.
Yeah, okay. Okay, I will start now again. Hope you all got the big overview of application of remote sensing and GIS in agriculture and soils through various case studies. Now, I will speak, then I will take only one nutrient, now nitrogen only, where you can see, where I will show you the use of proximal sensing for nitrogen management in plants. Because you know that in world soils, nitrogen is, nitrogen fertilizers applied a lot. And we need to, make big good strategies that affect, that can help in management of nitrogen in agriculture. So I will show you how proximal sensing, because I was talking about remote sensing, because you know that remote sensing is from distance, but for proximal sensing we use system that collect information near the surface, and these are available sensors where we can use all these sensing a range of soil properties like this one. If we want to identify electrical conductivity, potassium, cation exchange capacity of soil, pH, nitrogen, organic matter, clay content, and water. So these are the list. There are available sensors are there which may help in assessing a range of soil properties. You know, there are mainly two methods for assessing soil nitrogen. Either you do the remote sensing or through proximal sensing or spectroradiometer. For remote sensing, either you use multispectral data or hyperspectral data. For soil, because how you do the for soil nitrogen? Again, remote
Sir,
sensing or proximal sensing is not
sir,
possible.
Excuse me,
Hello?
sir. Are you sharing some screen?
Yes, ma'am.
Nothing is visible, sir. You have not shared.
Oh, sorry, sorry. No? Can you see the screen here?
Yes, sir. It is coming now.
Sorry. Sorry. Again, I will repeat now. Sorry. Proximal sensing, I explained. Proximal sensing is it collect detailed information near the surface. And these are the available sensors which can be used for assessing a range of soil properties.
Excuse me, sir. I can't see it. It is completely dark now. Can
Dark
anyone?
now? Hang on, ma'am. Should I hang on, ma'am? Should I join again? Hang on, ma'am. Hang on, ma'am.
sir,
Yes, ma'am.
sir, your screen is not visible, sir.
Yeah. It doesn't.
It is showing that you are sharing screen, but it is not visible, sir. What are the...
Hang on, ma'am. Again, I will share. Hang on, ma'am. Again.
Okay, sir.
Again, ma'am. Ma'am, you can see screen now.
No, sir.
You can see. Hello, ma'am. Hello,
Sir, the
ma'am.
text is Rajsetya has started screen sharing, but it is completely black. There is no content visible to us.
Hang on, ma'am. Then what I will do, I will join again, ma'am. Sometime internet creates problem. I will join again. Hang on, ma'am.
Okay, sir.
Ma'am, can you please screen now?
Sir, again,
Hello?
it's looking like that only, sir.
Pardon?
Sir, again, it is showing that you are sharing screen, but completely black it is, sir.
Oh my God. What should I do now? Again, I will.
Leave meeting and rejoin meeting, sir.
Yeah, I will do again. Yeah. Hang on, sir. Post disabled screen sharing.
Ma'am, please make him a host
Yes,
so
sir.
that he can share.
Post disabled participant screen sharing.
Yes, sir.
Post disabled.
Sir, we give the permission now, sir. Please clear it.
Ma'am, can you please see now?
Yes, sir. It is visible now, sir.
Thank you, ma'am. Thank you. Sorry, I am extremely sorry. Sorry. You know, we were talking about remote sensing and proximal sensing. Proximal sensing is because we know the difference between remote and proximal sensing. Remote sensing is sensing of information about an object or phenomena without coming in direct contact, and it is from a distance. Proximal sensing, this collects detailed information near the surface. These are the list of available sensors which can be used for assessing a range of soil properties like soil property, water, clay content, organic matter, nitrogen, pH, cation exchange capacity, potassium, electrical conductivity, soil structure, etc. You know, if you want to measure soil nitrogen, you can do either proximal sensing or through remote sensing. In both the cases, you can use either multispectral data or hyperspectral data. But for hyperspectral and multispectral data for remote and proximal sensing, we need to do field work, because ultimately you want to establish a relationship between spectral data and soil nitrogen data. For that, you go, if I am talking about multispectral and hyperspectral data of remote sensing platform, then you need to do the field work on the date of satellite pass, where you take soil sample based on various either grid sampling, stratified random sampling, or random sampling. You bring the soil sample to lab and you measure the nitrogen status of soil. Then you extract the spectral values from multispectral or hyperspectral data corresponding to your sampling sites. Then you use either machine learning approaches or any other simple linear regression like approaches to develop the relationship between spectral values and measured nitrogen data. Then for the spectroradiometer hyperspectral data, first you need to process your hyperspectral data, where you use either any continuum removal method, first derivative, second derivative, or any other method, and then you derive the relationship between processed hyperspectral data and your measured parameters. Use your y variables, and then you develop models through machine learning approaches like partial least square regression analysis, artificial neural network, gradient boosted regression, etc. So you can do that. So this was all about soil nitrogen. But if we talk about plant nitrogen, there are various approaches for that. For plant nitrogen, either you use chlorophyll fluorescence, leaf SPAD, where you measure leaf chlorophyll content, and then you use for ground-based sensor, either you use spectroradiometer or you use any Yara and sensor green seeker. For satellite data, you use high resolution satellite imagery like QuickBird, Iconos, or you derived a relationship between the spectral parameters derived from ground-based sensors or satellite-based sensors, and then you develop the relationship between these measured parameters through various approaches. Then you can develop the relationship. Please, we have to remember that if we want to derive the relationship between soil nitrogen and satellite derived parameters, the ideal time for soil sampling is that when there is no crop growth, because satellite sensor should see the soils. If it is covered with vegetation, it is bit impossible to derive the relationship between satellite derived parameters and measured parameters. Now, I told you we are having the relation. We took the soil sample from all these 4 sites in southern India and western India. Then we use Sentinel-2 and Landsat data, and then we derived all these relationships, and what we couldn't find a significant relationship between spectral indices and soil properties. Now this was the soil nitrogen data. Now I am coming about the plant nitrogen data, because ultimately from where nitrogen is coming? It is coming from the soil. But because I told you the problem, the soil should be bare if you want to measure predict the nitrogen status. So, but when you use tissue and concentration, when you take like this Zhao et al, what they did was they took the ratio of reflectance between 405 and 715 and predicted the tissue and concentration. They were able to predict the nitrogen content of plants with this spectral wavelength, and accumulated how much nitrogen has accumulated in soil over a period of time. Then they took the ratio of 795 and 755 and they got R square of 0.695. This one you can see here, where you can see the relationship between whole plant nitrogen, phosphorus, sulfur, potassium concentration and canopy spectral reflectance there. So these you can see here you can see here, this spectra is for nitrogen, this is for phosphorus, and this is for sulfur. So with this one you can identify where the absorption peaks are there and from where which nutrient stress is there. So it helps to predict the nutrient stress with canopy spectral reflectance. Now, because if you want to identify various phenological stages, here you can see where this for wheat, there is crown root initiation stage is there. Here, you can see here with this one, you get the higher reflectance in NIR, but not too much. But with tillering, you can see here, reflectance is higher in NIR than visible band. Here, late jointing, maximum vegetation stage, flowering stage, you can identify the various stages through spectral reflectance. But with duff stage, where the crop is about to mature, again reflectance decreases in the NIR range. Here, these are the where the Beggar et al. They use ester data for site-specific nutrient management, and they use these type of indices: NDVI, SAVI, OSAVI, MCARI, MTV, MTVI, and they found that NDVI, MCARI, but MTVI was modified triangle vegetation index was more suitable than others for predicting nitrogen status of canopy, corn canopy. Again, this one, Suresh et al., what they did was they took LIS3 sensor. Here the LIS3 sensor where there are four bands are there, and spatial resolution is 23.5 meter, and the leaf nitrogen was reasonably predicted from the NDVI value that was derived from LIS3, and the relationship was 0.79. If we predict and nitrogen status and how we validate that. So what they did was they took Pscmrcet and Perry. What they did was they derived this chlorophyll based index from this formula, and they use rapid eye satellite imagery, and they predicted plant N. Here, this one, modeled plant N, and then they measured the plant N, and they got a relationship of 0.97. Because once you derive an algorithm that can be used in the forthcoming years on a similar field for predicting nutrient status, you have to have measured data for making algorithms. It is not like that if you develop the algorithm from another area and then you predict that. This may not be correct. So you should validate the algorithm, and if from a nearby area, and then if it is you are not getting good results, then you have to measure parameters in the lab and then try to develop a relationship. This is the theoretical relationship between NDNAI and NDVI for high and low chlorophyll nitrogen concentration. Here you can see where the CCE is 1, where the CCI is 0, all this there, so you can see all the relationship here. Here you can see here, because people are predicting NDVI or other spectral indices from the satellite data. But there is some point there where there is a saturation there. When there is a saturation, then your major parameters, and with your spectral indices, you can get a relationship between these two parameters up to a certain level. And after that, when there is a saturation here, like all these points here, then you means we have to be very careful of making any model. So this was all about multispectral and hyperspectral remote sensing can be used for detection of spatial variation in N status of the crop. Use of this technology has significant potential for maximizing the efficiency of nitrogen application. Thermal remote sensing has the potential to identify spatial variation in crop water status. But I already told you that soil background has significant impact on spectral and thermal images. So we have to be very careful when we are making model for predicting nutrient status of crops. Thank you very much. This was all about for application of remote sensing and GIS in agriculture and soil, and application of remote sensing and GIS in nitrogen status. Thank you. Now I'm happy to interact with you. Hello, ma'am. Hello, ma'am.
Ah, sir.
Ma'am, I'm happy to interact with participants now.
Okay, sir. Sir, we get the permission to unmute themselves, sir. Dear participants, you can unmute yourself and you can ask your queries if you have. Please interact with the resource person.
You hope you all got me what I was trying to say. I didn't use jargons to make you understand. Hope you all got the message about application of remote sensing in agriculture. And I didn't make it too long because I made the lecture in two parts. Because first I kept the generalized part and then for nitrogen part. Thank you, sir. Thank you.
Hello, sir. Hello.
Yes, sir. Yes, sir.
Vikram Singh Power Patil is here, sir. It was really nice session that you have delivered regarding to crop suitability analysis as well as soil and crop nitrogen analysis. Sir, I just want to know that is there any data set available regarding to soil chemical properties of remote sensing database?
Sir, what you can do is, sir, soil health card data is mostly available on Department of Agriculture, Government of India website. Okay. And they have written in which dates they have taken sample. Then, okay, sir, freely available multispectral data like Landsat, Sentinel is freely available. Yes, sir. Then you can download that data corresponding to that period, and you can use machine learning approaches to develop the relationship between soil health card data as well as your spectral reference data.
Yes, sir. Definitely, sir.
Yeah.
Sir, I was asking about land capability classification. Actually, I wish to study cadastral scale land evaluation for my village, and I wish to build a village information system, particularly for natural resources. So in that connection, sir, how do I carry forward, sir?
Sir, yes, sir. It is very good information if you are able to derive that. So the thing is, you need to have information about soil texture and other parameters.
Yeah.
And soil texture, I don't think that information about soil texture at cadastral level is still available.
Yes.
Then you need to do some survey, and then you will be able to derive this type of information at cadastral level. If it would be have any district or regional level, then you can use NBSS maps or other soil grid data that is freely available. At 250, sir, soil grid data 250 meter is also freely available. Then you can use that one.
Yeah, sir. I have explored already that soil grid data, but I am a bit confused regarding to the validity of because that data is on global scale, no? So direct use of that data, I think it will be overestimated.
Exactly, sir. But now the ultimate thing is you have to do survey. And after that, I'm more than happy to help you, sir, via emails.
Yeah, sir. Yes.
Happy to help, sir. How
Thank you, sir.
we have to take a science forward, and I'm happy to help, sir.
Thank you, sir. Thank you. Thank you very much.
Another question for participants. Another question from participant.
Hello.
Yes.
Sir, myself, Dr. Ravi, sir, from HOD and coordinator of this program.
Good morning, sir. Good morning.
Good morning, sir. How are you, sir?
Fine. Thank you, sir. Thanks for
Thank you,
giving me an opportunity to speak on the application of remote sensing in GIS.
Sir, it's my pleasure, sir. I would like to thank you because you, even though you are having hectic schedules and all, you came forward is for sharing your knowledge, and it will be help to the indirectly society, sir, because you are helping to the faculty members. It's a faculty development program. So automatically it will be reflected to the students. From the students, it will be get the benefit to the particular society, right, sir?
Yes, sir.
So,
thank you, sir. Thank you.
but once again, I will tell you that thank you so much. You are showing concern unto our department and our institution, sir. Definitely, I will be in touch with you, sir.
Okay, yeah, sure, sir. More than happy to collaborate, sir.
Sure, sir. Definitely, I will call you and I will talk to you personally, sir.
Yeah, sure, sir. Sure. Thank you, sir.
Sure, sir. Once again, thank you, sir. My camera is at my laptop camera is particularly not working.
No, sir. No worries, sir. No worries. Not
Sure,
an
sir.
issue, sir.
Once again, thank you, sir. Thank you so much.
Thank you, sir. Thank you. Thank you.
Thank you,
Kirana,
sir.
madam, please go ahead for the next.
Yes, sir. Thank you, sir. Thank you once again for accepting our request.
Okay. Thank you, ma'am. Thank you.
Thank you, sir. And thank you all the participants. Next session will start at 11:15 a.m. sharp. Please join 5 minutes before the start of the session. Thank you all.
Recording in progress.
Good morning, sir.
Good morning, madam. PPT
Hello, madam. Hello.
Sir,
Hello.
sir, chep.
Yes, madam.
Hello, sir.
Madam, Ramarao sir was joined, right?
Yes, sir.
Okay, madam. Okay. Sir, good morning, sir. Ramarao sir.
Good morning, Ravi garu. Thank you.
How are you, sir?
Fine, బాగున్నాండి.
బాగున్నారు సార్. థ్యాంక్ యూ సార్. కానీ కొంచెం ఇబ్బంది అయినా పాపం మా కోసం వచ్చారు సార్. పార్టిసిపెంట్స్
థ్యాంక్ యూ ఫర్
చాలా బాగానే మోటివేట్ అవుతున్నారు సార్. బాగానే రెస్పాండ్ అవుతున్నారు కూడా. సెషన్ కూడా మనం ఇప్పుడు జరిగిన సెషన్స్ కూడా చాలా బాగానే ఉన్నాయి సార్. అంటే పార్టిసిపెంట్ అంటే వాళ్ళ దగ్గర నుంచి మన ఫీడ్బ్యాక్ వస్తుందంటే if we got something feedback from the participants, they are enjoying a lot. Even though, thank you sir, thank you so much, because even though you're having hectic schedules and all, but you came forward and you are helping to the society indirectly.
Thank you for, we'll be happy to be interacting. I think if I can request all of, at least why not we have at least for some videos which
there is some formality is there to introduce you.
So I am requesting the participants,
Madam, please you go ahead.
They can turn on the videos, because
hello madam,
talking to your monitor is very difficult.
hello madam.
Yes, sir.
Madam.
Sir, shall we start, sir?
Yeah.
Yes, you go ahead.
Thank you. Welcome back all the participants for the day 4 section 2 on advanced targeted remote sensing applications using classical and ML approaches. I also extend a warm welcome for this section keynote speaker Dr. N. Ramarao, Professor IISP. Thank you for accepting our request, sir. Now it's my privilege to introduce this section keynote speaker Dr. N. Ramarao Garu. Dr. Ramarao sir is a professor in remote sensing and image processing in Indian Institute of Space Science and Technology, Department of Space, Government of India, Thiruvananthapuram, a visiting professor of University of Kausal and Libizin Center for Agricultural Landscape Research, and has been Alexander von Humboldt Research Fellow, Germany. Dr. Ramarao obtained MTech Remote Sensing from Birla Institute of Technology, Metsa, Ranchi, and PhD from Indian Institute of Technology, Roorkee, and Hyperspectral Image Processing in 2006. After a brief stint in RMSI Private Limited as a project leader, Dr. Rao moved on to continue academic pursuits in RMIT University, Australia, and Libizin Center for Agricultural Landscape Research, Germany, as a research scientist during 2007 to 2010. During this period, Dr. Rao performed research studies on hyperspectral image processing and analysis methods and developed several new hyperspectral data analysis algorithms. Results of these studies are published in several peer-reviewed journals published by IEEE, Alastair, Spring, Tyler, and Francis, etc. It has been an active member of several professor societies, including senior member of IEEE, and it is the founder of chair of the IEEE Geoscience and Remote Sensing Society, Kerala chapter, and chairman of the Indian Society of Remote Sensing, Kerala chapter, composed of several doctoral and master's students. Dr. Rao's research team has been working on the real-time classification, automation, target detection applications in military, agriculture, water, and forestry using high and ultra-high spatial and spectral resolution, remote sensing data from terrestrial, drone, airborne, and satellite, lidar, point cloud, 3D modeling of the natural and built environment, open architecture, and regional sensitive atmospheric correction, model with multispectral and high spectral imaging across platforms have been some of the established specialties. Now I request Dr. N. Ramarao sir to take over the section. Thank you.
Thank you, madam. Thank you very much. Thank you, Dr. Ravi, for inviting me. Am I audible clearly?
Yes, sir, you are audible, sir.
Thank you. I like to talk something more of a very specific nature of remote sensing, which itself is some sort of interdisciplinary in the sense applications are not necessary to be always looking into the sky or from the sky, but sometimes we can look around, maybe both on the ground as well as indoors, and find that many techniques that we think only satellites do can be done even from a ground level platform. Or the things that we think that satellite can do are indeed not necessary to be done by satellite. So from a practical perspective, we like to do some other things. So that way, my topic is more of some selected target applications in the sense and traditional approaches that we call classical. And I use, instead of ML, I use MI. If the machines learn, humans forget. So we don't want to be forgetting ourselves. So we can say machines can intervene somewhere, but they cannot learn. Okay, so let us keep the learning with the humans, and the machines can intervene some technological inputs. So that way, we still prefer to use the traditional way of man and machine. So they are tools, but not replaceable. Then most of the things that we do cannot be done by individual faculty member, but as a group of students, mostly PhD students and some of the master's students. So I always owe a lot to them, and I acknowledge their contributions and everything. And just coming to this particular kind of content, with some example things, I like to present something on this targeted remote sensing applications. So there are some 3 to 4 kinds of applications which we could consider some representatives of the things that we like to put from a targeted perspective. So the domains are quite different. In the sense, applications are very, very different. For example, it could be agriculture, then water, then altogether some sort of military perspective. In the sense, we like to be in that way, but we will be starting there. So applications are quite different, and what we like to know is that it's not necessary that we are actually solving a problem, and it's not a kind of an operational application development, but trying to see the potential of advances in remote sensing to venture out for such kind of intervention. So that is the aim of us. And so in that way, we like to have some definitions of targets. In the sense, what is targeted means the targeted, it includes the target. So in that way, what is the target? How we define them? What are the different approaches of looking at the targets in remote sensing data? And perhaps some applications which would be exploiting this kind of properties, what we like to. As I mentioned, these techniques included both classical as well as machine intelligence kind of techniques. So it's a combination of the things. And as I mentioned, targets are quite different. So these are the something that we are going to be finding it. So as a function of target, as well as the platform from which we actually sense. So it's a combination of multi-sensor, multi-target study applications, a kind of thing. I presume that most of you are familiar with the remote sensing principles, at least the basic principles. Where do we sense? In the electromagnetic spectrum, typically the optical region where we start at 4,400 nanometers and end up 2,500 nanometer is a region which is very dominant for optical region, and going little beyond thermal infrared region, and in the active remote sensing we have got this microwave portion, which is itself is a completely different mode of imaging. So you will find different ways of sensing radiation in different periods of electromagnetic spectrum. So objects quite appear themselves to be quite different in different regions of the electromagnetic spectrum. So in this particular case, we'll be mainly concerned on this optical electromagnetic spectrum. So that said, most of the images are acquired within the, let us say, 400 until 2,500 nanometers. And of course, there is one active remote sensing as well that we'll be finding it. I just like to remind again that in this optical remote sensing, what a remote sensor measures as a function, or you say as a primary parameter of energy source, is the reflected radiation. So the energy that is to be measured is the reflected radiation. So scattering is the process which derives this kind of reflected radiation, and the range of this scattering and hence reflection radiation as a function of objects interaction is not something like very deep. Always remote sensors, particularly the reflected radiation based remote sensors, are shallow sensors, in the sense the interaction of radiation with the object not necessary to be order of several meters into the object. So it is very shallow. Most of these radiation come from the surface properties. So surface, top few millimeters or few centimeters at most. So we call it mostly surface sensing. So by understanding surface sensing, we like to interpret or infer something about subsurface properties of objects. So that way, reflection is the primary property that is going to matter, and the variation of these reflectance as a function of wavelength is the key which imprints the kind of object-specific physical and chemical properties. So different objects will have different sorts of spectral interaction features. So by measuring the radiation in multiple wavelengths, you like to interpret the nature of objects as a consequence of their reflectance differences. So that is the primary property of remote sensing. In principle, theory says that all sorts of materials have very distinct spectral signatures. So this spectrum curve is what your signature. No, the theory says that one, but we know that it is rarely followed than actually happen. There are some cases where we like to see both the possibilities. Then, depending upon the kind of levels of energy and the kind of sensors that you do, in the sense how many number of spectral bands that you can measure, and what is the information gain while you like to increase your number of bands in a remote sensor, is a function of objects existence. So with a primary level of detection of an object in a remote sensing image to the level of quantification, quantitative estimation of the properties of objects, that includes its identity, its physical and chemical characterization, what you call it quantification, requires a whole lot of different kinds of spectral bands and different kinds of algorithms. So if you have got, let us say, multispectral imagery, order of some 10 bands or 15 or 20, then you can actually go up to the level where you can differentiate and discriminate very well. So You will not able to establish unique identity simply by saying that holding the spectrum and trying to find out its identity is not possible. But you can actually differentiate it and discriminate it statistically on limitations. So theory it is there, and you find that a lot of those images are also nowadays available. So you can see that the possibility for us to play around with objects is ranging from its detection. Detection does not necessary to be naming it. Just as whether something is there or not, or something is an object or not, is called detection. And if you are going to describe it fully, be it a chemical composition and geometrical structures as well as a label, then it is called quantification. So the details vary in between these two extremes. Generally, in remote sensing analysis, there are actually few categories that we call, depending upon the way you think, the kind of application you do, and the resources that you can deploy, the potential resources that you can deploy. Actually, you can put two perspectives. One is something which is very static. For example, if you are willing to map, let's say, land use land cover, or let us say finding out area of a crop, or the crop acreage at national level, or just for the sake of forest map or soil map, or simply finding out how much area is under urban built up. So if these are the kinds of applications, then those things won't change radically. So the system itself is a static. Then what happens is that you get the images at your convenient time. You have got access to a very nice laboratory. Lot of powerful systems are there, and you can come to the office, just stay for several days and leisurely do your work and get some output. So that is what you call it a static and rework kind of application. So the work itself is not necessary to be time critical. So there is a system stability in the sense of the system that you like to map or understand, and you have got access to a host of infrastructure which included both machine and human infrastructure. So there is no hurry that you need to do something in, let's say, by a second. So you have got a lot of such kind of application. So one type of application setting like that. In other category, what happens is that the things are not something like at your convenience. For example, if some kind of flood is happening and if the situation is live, so you like to see in the next half an hour which are the areas that are going to be submerged, or you like to find out what is going to happen in the next half an hour, or situation is something like where a farmer likes to apply nutrients, crop nutrients, be it fertilizers or any other in chemical insecticides, based on the plant's condition in his field. If he likes to apply a sort of remote sensor technology, then what the situation that demands is that you don't have the luxury of waiting, for several days to get the data and comfortably analyze and give the results. No, the things have to be done on the go. That requires you that right from data acquisition until the results computation, the results presentation, the time is very critical. So order of maybe seconds or at most minutes in some cases. That includes certain kind of situation. For example, the application is some sort of military situation where you need to map on the go. Then the things that you will be finding around is that you need to derive the outputs not by days but by minutes and seconds. So in the sense, as soon as the data are acquired, and we know that the computers and image systems these days are very, very sophisticated. You get few hundreds of images by every minute. So if that is the data rate, then the kind of capability for you to convert the data into information, that is analysis of the data, should be also matching with the kind of thing. So that if you call as dynamic and stream processing applications, then you will have a lot of other kind of limitations as well as opportunities. Limitations are that you cannot have your laboratory taking to the sky. So you will know it. The computing is something. It comes the first thing that you will not be having very sophisticated computers to deploy for that purpose. And second thing that comes is that human intervention. As a land use land carbon, you can take several days and give some output. But here that is not going to be there. Perhaps you are not even able to intervene even for a second. So human intervention is really minimal, or I would say nothing. And the computation time, as I mentioned, almost near real time. So it could be seconds or even a fraction of that. And then the data rates would be much faster. So every second you may get some 100 images. So you will now have to deal with this kind of situation. So these are the challenges, and the opportunities are many. If you are able to come up with a system which can be responding to this dynamic and stream processing kind of capability, then obviously the kind of application that you can derive are really many. So it can be industrial application, it can be real-time monitoring of environmental compliances, or even several applications in agriculture, or several air monitoring, or so many. You will get a lot of possibilities that included a strategic application. So applications are many, but capabilities are also very hard to find it out. So under these two conditions, the reality is always in between these two. The first one is you are comfortable. The second one is machine comfortable, but you will be finding it if you say. So in the both the cases, what we like to have is some sort of targeted information generation. So that requires us to define what do we mean by a target. Okay. So you can say target can be anything. Let's say if I'm looking out for areas where copper can be mined, in areas where potential copper is there, then that particular patch of land itself is a target for me. Yeah, I think some background noise is there. If some of you can switch off your microphone.
అదైతే పర్లేదు అలా అయితే వీళ్ళు ఎంతో కొంత బెనిఫిట్ ఉంటుంది బిల్డర్స్
హలో
10 కిలోమీటర్లు అంటే పర్లేదు.
Thank you. So for strategic applications, some sort of military hardware itself is a target. So he or she likes to see the existence some sort of specific hardware in the area designated. So that itself is a target. Or for me, sometimes recently I would say, if a plastic body itself is there, let us say some sort of debris which are flowing along with the water, that itself is a target for me to find out how they are actually polluting. It can be anything. So many things, or even for a farmer, target can be areas of his field which are suffering with some sort of let us say plant disease, or where a location where a particular nutrient is not yet applied. So you can have a lot of those kind of targets. So if you like to map, or if you like to identify them, then that is the question. As I mentioned, remote sensing involves a lot of the things. So the basis is always, let us say, if you are going by optical thing, okay, so where this optical intensity and derived reflectance, so you are able to find it out. The biophysical and chemical properties are the dominant sources of the reflectance. On the other hand, if you are going by the kind of geometrical kind of remote sensing data, for example, LiDAR, GPR, stereo images, or even SAR, then what happens is that the dominant features are actually structural features. So visible and structural features are the ones which contribute to the kind of signal. So you may not be getting, let's say, reflectance, but you get a lot of the geometrical features. So a combination of the techniques that you will be finding out when you like to deploy for a targeted remote sensing. And obviously it is a function of the three cases. What data that you like to have, at what data, in the sense the nature of sensor, and the platform, whether it is satellite or airborne or drone or ground or under land, and the kind of algorithms. So what kind of problem that you're going to find out? Is it a kind of dynamic modeling, prediction, or mapping, or mixer modeling? this some sort of or matching, and then at what kind of pixel scale, is a full pixel or subpixel or even very trace of it, or an aggregate of pixels that you call object. So different levels of it there, and then lot of corrections and processing sequences make you to have an application derived. So you need to have some sort of control over data, algorithms, and the inherent processing scheme. So when you mix up the things that you need carefully choose these combinations of the three things, then perhaps you are going to find out some applications which are very targeted. If I like to have, for example, this kind of target detection in hyperspectral imagery. For example, hyperspectral imagery, nothing but a in optical remote sensing. The key difference is that this electromagnetic radiation is sampled in few hundreds of spectral bands and maybe very narrow bands, and sampling is done very continuously. So that way you will get a full spectrum of electromagnetic radiation interaction with interacting with objects, and perhaps you can have a full spectrum of information about object's footprint in the electromagnetic spectrum. So perhaps the diagnostic spectral features of different objects can be recorded in this kind of hyperspectral imagery. So that way you can say that if an object has very specific spectral footprint, then that can be tracked with the hyperspectral imagery. So this hyperspectral imagery is the source of the data, which potentially gives you that full spectrum information. But remember, it is a potential source of full spectrum information. So potential information. So if you are going to convert that potential information into an interpreted information, then the problem is solved. But we will find that it is not that easy to convert potential into actual information. And within that, we like to say define what actually we mean by a target. Be it hyperspectral or any other kind of images, target detection is something like we like to find. As I mentioned, target can be anything. So for example, if I have a particular sheet of metal and which I dropped somewhere, okay, in a particular area, and using this remote sensing instrument, I like to find it where that particular metal sheet is there, where I would have dropped it. So if I acquire image over that potential area, maybe by aircraft or satellite or even drone, then by simply giving the property, spectral property of that particular metal sheet, if I can identify in the image saying that this is the location exact metal sheet in this area, then I would have actually detected my target. So like that you can always have. So as such, you can have detection, how you will be able to detection, and what are the basis for it. So in general, there are two ways of looking at target from a spectrum and remote sensing perspective. One is purely spectral properties. It's a reflectance properties. What is the signature or spectral signature of that particular target you are looking out for. And you like to find that particular spectral signature in the area which is imaged by a particular remote sensor. So it is a simple case of matching. You have got only one spectrum, so find out the occurrence of that spectrum in the image. So how to find out the potential occurrence of that spectrum in the image is the problem there. Then the other way is looking at it is that statistically finding out the potential areas which are the sources of these kind of targets. So you are not having an idea about what is the spectrum of material that you're looking out for. That means you're not sure what actually you're looking out for. So when your target itself is a little bit ambiguity in the sense unknown to you, then what happens is that you're looking out for something, but you are not sure what you're looking out for. If that is the situation, then the kind of approach that you will be taking out for remote sensing is the two things that you call. One is this anomaly detection. In the sense you are going to detect somewhere in the image which is anomalous, exhibiting anomalous behavior. So you call that anomaly detection. And once you identify the regions of this anomalous behavior, perhaps studying in detail more on the same anomalous area with additional information available at that time, perhaps you are able to find out what the target it is. Otherwise, you are looking out for some distinct nature of some area. So a background in the some foreground, which is quite different to the background. So that you call some target. Then you are going to label it later. So the cases of something for which you have prior information of the spectral behavior, then the cases which you do not have any spectral features or spectral knowledge, as well as you are not sure what you are actually looking out for. So, but you like to know if something is happening in this area. So what is happening you don't know, but you like to find out if something is happening in this area. That means some background is being now disturbed. So you like to find out areas where this background is going to be disturbed, where the homogeneity is going to be disturbed. So that is the case of background detection, background disturbance detection and anomaly detection. So in the first case, the question is something always like this. I have a spectral signature, then I like to know what is the nature of this particular material. Is it related to a rock or plant or chemical or something? So if you are going to use such kind of question to answer, then you have got a prior knowledge of spectrum, and you are most likely to find out the occurrence of that kind of spectrum in the image by identifying the pixels which match with this kind of spectrum. So that means you will have got a source of a library where you have got spectral signatures of different materials stored in your database, and the case is a library search. So now the target identification is kind of spectral library search. So if you see that there are hundreds of spectral libraries which are recently available, you may find a lot of them. Okay, so the purpose is this to exploit this kind of theoretical facility. So the things are there, and we find that it is no easy job. So potentially simple, but very complex in terms of the diversity that you can find it out with the material. You find a lot of such kind of things. And then when your source is just an image, then if you are referring to an image analysis and a targeted mode, then you are looking out for the existence of only one thing. So you are looking out from the possibility of n number of information classes imagery. You are looking out for the possibility of existence of only one category. So if you go that way, then it's a targeted kind of information mode. Of course, now if you see the kind of remote sensing imagery, these are very, very sophisticated. So you get a photographic quality kind of remote sensing data as a hyperspectral imagery, a full spectrum imagery with the spatial resolution, which is also very, very high resolution imagery. So these are the things that are there. So when you have got quality of data, which is something like this, then you can have applications which are quite different. For example, I can apply even for agriculture, where instead of talking about crops and fields, I can talk about fruits and vegetables and something like that. So I am now going to be identifying information at individual unit level. So if such kind of detailed knowledge can be interpreted for remote sensing, then you will have got a lot of potential to find out a targeted kind of modes. And as I mentioned, the targets are really very, very diverse. So for me, crop targets are something. If I like to find out the occurrence of a particular crop in some area, then I say that my target is identified. Or for different people, it's a different person. So finding out the existence of these kind of things and the approaches that you like to use is the major emphasis of this target detection in remote sensing. And by imagery, it is something like finding out very few pixels, identifying pixels which are very few among thousands of or lakhs, actually not thousands, but millions of pixels. So a target can be something whose spatial distribution in the imagery is very, very low. In the sense, the occurrence of pixels which are less than 10 for each million pixels of image, if you are going to find out the occurrences of just a few pixels, which represent the kind of object you are looking out for among few millions of pixels, then that kind of identification that you do to find out very few pixels is what you call is a target detection. So the things other than the few pixels that you're looking out for, every pixel in that image is a background. So it's not actually something like a ground, but you consider that as background because you are looking at only very few pixels. So when you like to do certain kind of target detection experiments, you like to find out your algorithm output should be identifying an image with only these few pixels are actually in the image and all others should be black. All others should be like a background, uniform background. So that is the case that you theoretically expect as a kind of thing. So if I am using the spectral properties, then what happens is that it is a case something like this. So I have a target. For example, I like to find out a particular kind of sheet here. If that is there in this imagery, in this area represented as imagery or not. And I have a spectral signature of that particular material for thing. So my now case is finding out the existence of this particular pattern in this entire imagery. In this imagery, there may be, let's say, a couple of millions of pixels, and this is only equivalent 1 pixel. So trying to find out the occurrence of this particular pixel equivalent in these 2 millions of pixels. And if I can find out the regions where this particular kind of spectral behavior is observed, then that is the target identified. So this is one kind of detection mode that we have been extensively working on. And then it's a case, how you perceive that particular target from different platforms. For example, it's a case of, let us say, imaging platforms and algorithms, and also the case of processing, because in between your target and your sensor, if the sensor happen to be airborne and satellite, then you get a lot of other environmental interventions, which included atmospheric disturbances, sensor noises, and other surfacial disturbances. All of them would be showing the target signature as quite different to its original behavior. So you need to do a lot of those kind of intervention removals, and then finally try to find out where that particular target is. Mathematically, we can actually have this target as a binary hypothesis. So if I have some kind of behavior, let us say my hypothesis is something like this. Whether this signal is there or not. If the signal is present, then my hypothesis is alternative. If the hypothesis is such that the kind of signal is equivalent to background, then it is a null hypothesis. So it can be a kind of binary hypothesis testing. If you like to define target detection in any imagery, it's a binary hypothesis. Either a pixel is a background or a target. So how we are going to label a pixel as target or a background is the one which will be defining the kind of algorithm. So what kind of algorithms that you like to use to do this kind of verification job is the detector. So those kind of algorithms, if you call them target detectors, then using different kind of target detectors, you like to find out what are the targets in imagery. And as I mentioned, we tried with 3 to 4 kinds of application areas. The first one we tried with is agriculture, because for us, this is also one of the very interesting area which can have multi-dimensional applications, which included both the farmer level as well as the governmental and other banking or other sectors level intervention. So if I like to find out areas in an agricultural field, the field is not necessary to be order of several thousands of hectares, but order of, let's say, 1 acre or even less than that. So if I like to have some sort of algorithms, maybe targeted remote sensing algorithms, wherein I can find out at a particular plant location what is the nitrogen status. Or if I can predict if at this crop growth stage, the yield will be something like this. So if I can give this kind of annotated information from both images and statistics, then the applications are quite different. So for this, there are two critical things that require for us to have this kind of, targeted kind of remote sensing applications in agriculture. The first thing that comes is the mapping. In the sense, you need to identify then what kind of plant you are looking at. So instead of saying this rice crop, you will be finding out if this is a rice crop. Okay, first label is done. Then in this rice crop, in this patch of the field, it is a patch supplied with, let's say, excessive nitrogen. Okay, so if such kind of differentiation is done, then the application that you can derive is, are numerous. But what happens is that logically you always get difficulties from nature as well as from technology. What actually nature gives you that sometimes they are actually very similar in remote sensing data. For example, if you look the signatures of, let's say, sugarcane and maybe rice, they may look by spectrum very similar. So that means your remote sensing sensor may not be looking them as different. They think that both of them are either sugarcane or rice. But for us, we know that these two are two different crops. That means your sensor actually is limited to differentiating. Sometimes spectrally different, but structurally same. For example, if I look at rice crop and maybe some other crops such as, let's say, wheat or barley, spectrum may be looking quite different, but by structure they are very similar. So if you look at, these are the two different things: structurally different, spectrally similar. So spectrally different, structurally similar. If these are the conditions that actually existing in the nature, then how do you deal with the identification problem? Using remote sensing is one of the toughest problems. So where if the solution itself is a commercial application. So apart from that, you can also have some sort of algorithmic schemes wherein you like to predict the plant level growth. Let us say today the plant is, let's say, some 35 centimeter height. After 10 days, how much height is going to be for this plant? So if you are able to precisely predict for that, then you will have a lot of potential applications which will be deriving that. So how you are going to use this remote sensing data and the kind of algorithms which would answer some of these situations are the ones which we call some of these targeted remote sensing applications. So I can go on and very detailed into these, which are the problems of so many kind of things. Remote sensing technology application, agriculture is so much. In the sense, you can have a lot of applications. But at this moment, we actually started dealing with the plant level. So not at the field, but at the plant level. And we like to see two problems. One problem is the estimation problem. The other one is the identification problem. So these are the two examples that I like to share. As I mentioned, every information acquisition is a function of the sensor. So you have got a lot of sensors and capabilities. Now the multispectral remote sensors or hyperspectral remote sensors, spatial resolution you may find even let's say 10 centimeters, and the number of bands even could be few thousands or few hundreds at least. And then geometrically you have got LiDAR and SAR, which will be giving you point density and like another polarization metric. So the kind of features that you get, both spectral, geometrical, and other interferometer light intensity features, are the ones which actually contain different sorts of information. So for the case that the first demonstration application, we are going to see the agriculture application, and the data that we acquired was actually pertaining to an agriculture plot that we laid out in the University of Agricultural Sciences, Bangalore. So in this one, we have got some experimental setup wherein we have grown 3 different crops with different types of nutrient treatments, and then we acquired multi-sensor data, which included drone-based hyperspectral imagery, ground-based hyperspectral imagery, and then LiDAR scanner, 3D point cloud that you call, which are all done concurrently, and this data formed the basis for us. As you can see, these are some typical photographs of our experimental setting. And now our first target is actually, can we identify these fields label these fields at the plant level. By our normal view, if you see this, all these fields are actually at the individual crop, plant level. Cabbage is a plant. Similarly, even this, let's say tomato, when it is growing at this level, or even let's say this brinjal, is an individual plant. So, if you have got this very high resolution data, which covers this kind of images, then can we automatically identify label of this particular crop at individual plant level? That is the question. So data were acquired at multiple growth stages, and a huge database of these images and appropriate ground truth data were actually acquired, and we tried to put out for applications of some recent evolutions. So the things that we always call it is, let's say, recent development is like a say deep learning approaches. The idea is that if we have got an image which is taken from a drone, which may contain images in the sense plant objects at a different growth stage, and the network that you would have actually trained could be tuned for so many kind of crops and at different growth stages. So we have prepared a network which is a very detailed network of different form, and the images were actually used for training were containing all sorts of crops in the sense in the experimental stage, and crops of different growth stages were used for the training data for this network. And the testing is something like that. As we alter the input images, then we should be deriving the input output as it is a annotated object. So the nature of that particular plant, this is identity, as well as its nitrogen level is the anticipated answer for it. So for example, sometimes image may contain a single object, yet you need to have the output which refers to the kind of object only. Sometimes the image may be containing multiple plant objects and which are disturbed by a lot of scale distortions and other noises. Still, the output should be differentiable, should be decipherable. So that way you can see that the kind of application where we try to map, for example, a tomato plant, and the mapping is done at due to plant level, and the architecture is trained for a host of plants and a host of let us say growth stages. So you like to find it out its performance by mapping at the plant level. So that is the targeted level identification of crops in a drone based imagery. And it is the case when we like to have this brinjal eggplant as the imagery input to the network, then it's a potential outcome. So you can see some sort of noise is there, but some potential information is also there. Then what we tried is that if this is the initial stage, then it is working. If we have images which are actually referring to very grown stage. So for example, this is a crop where two crops are there. One is this, let's say, brinjal, that's eggplant. The other one is actually tomato, which is almost, in the maturing and harvesting stage. Then we try to map these two crops at a potentially individual level, and where no human intervention is there. So it should be completely automated imaging. This is one example. For example, if the input image contains, let's say, 3 different crops, crops of 2 at a different area, then how that particular network behaves. It can be a case of, let us say, a particular crop is dominant, other crop is, let's say, minor. So in the previous case, one crop is dominant, let's say brinjal is dominant, tomato is minor. In this image, this scene is reverse. So how is this particular network performing is also has been tested. So like that, different kind of thing. So this is an image where the scene is to map 3 different kind of crops. For example, this is a cabbage, this is a brinjal, and this is a tomato. So the network should be responding to map these crops at the individual plant level by varying different kind of proportions of different crops in the images. And when we say different proportions and different crops, it is intended that the height of that particular plant is, in the sense, the imaging done is obviously quite different. So we've flown that drone at different heights and acquired different images. So the combination is always there. For example, this would have been acquired, let's say, at 40 meters, and the next image would have been acquired at 100 meters. So, like that. So, you need to see when you get different scenarios of image, then how is that responding is the question. So, mapping of crops at individual plant level is the one which we try to demonstrate with this deep learning kind of architecture. So, this is single crop application of cabbage mapping at plant level. And again, as I mentioned, different cases of it. So we will find that somewhere some things are better, but when some crops, if you see, for naked eye, this tomato looks like maintaining some sort of structure. But in our mapping, you find that is very much blurred. So the problem is that lot of interventions of the background and maybe the gaps of the canopy of the plant is so huge that the entire background intervention or background corruption is so much high in the case of this tomato. Whereas, let's say if it is a cabbage, the plant architecture is very specific. So you may not be finding gaps within the canopy. It may be having a distinct profile. So you still find it out, its structure reflecting in the output as well. So that indicates that you need to see that this possibility is not something like generalizable across different crops, but maybe some crops are better done than other crops. And then the second application that I am going to derive is actually not this imagery, but another sort of remote sensing data, which we call point cloud. So LiDAR data or laser point cloud, which is a discrete point cloud of different points. So instead of a regular grid-sized kind of raster images, now the data are something like a disorganized point cloud. So it will be only points, and every point is an independent point. So there would not be any logical connection between or among the point. So when your entire landscape is seen as an amalgamation of different points, so now you need to find it out using any kind of algorithms to turn the points into information and potentially structures. So something like, connecting the dots and making the object is the question here. So it is a kind of scanning mechanism where LiDAR sensors are usually scanning and they may penetrate. So advantage of this LiDAR is that it is a direct 3D, potentially 3D data. So range is the measurement which is done, and advantage is that the radiation is a laser radiation, so it can penetrate through gaps in the canopy or any other shadows, and then it can hit the target is much deeper compared to a regular surfacial images done, which is the optical case. So that way, this LiDAR is much more potential in terms of finding out the geometry of surface. So as I mentioned, the point is something like this. The data looks like something like a kind of point. So, and the data are nothing but X, Y, Z. So X and Y are your geo coordinates. It could be, let's say, lateral longitude, and the other coordinate is the height, or you can say, let's say, range. So these are the only, let's say, data point that you get. Now you need to convert this entire point cloud into an information cloud. So this has to be converted. If you're able to exploit that, then perhaps you will have sort of, a lot of targeted application. For example, we tried some sort of these typical pattern recognition approaches. We try to convert this point cloud into an intermediate product, then finally a labeled product. For example, if you see this is an image and it's a LiDAR point cloud. Left side is multispectral image, so aerial imagery, and right side is point cloud. So this pertains to an harbor, a kind of seaport, and it is the point cloud. Now you can see this point cloud. Every point, there may be a few millions of points, but every point is an independent point. So you need to establish a lot of connections, lot of neighborhood, and then maybe object detection, then finally labeling of the points as belong to different information classes. So for that, we followed quite different kinds of image processing, which included 3D segmentation algorithms after supervoxelization of this point cloud. So initially, we prepared some sort of intermediate objects, which we call voxels, pixels are in the volume. Because the millions of points are very difficult to process, so intermediate level of before we do segmentation, if we can aggregate them as some sort of objects, then that is easier. So it is some sort of let us say, what is that, clustering, but in the three-dimensional space. So when you have the clustering done in the 3D space, then you call these voxels, and the approaches that you call them is supervoxelization. And so you can consider them as the cases for further segmentation approaches, so that you will have an intermediate level of outcome of the point. So now points which are individual discrete objects in the original data are now connected. So when you have this segmentation done, there is some sort of neighborhood and belongingness established. So the next step is to label it, to identify label for it. So maybe a classification can do. So once you have that, now the classification is done, wherein every point is given an appropriate name. So all the points are now logically connected and potentially information sources. So you would be knowing by the label what it is. And if it is ending there, then it will be an intermediate outcome. But what we want is some sort of reconstruction. So from a different perspective, the classified output is still a point. It is not something like which will be looking nice for you. So though it is labeled, but it is still a point. So for us to derive structures is something beyond. So if you have got the 3D surface recovery, then the kind of points which are labeled are ultimately going to be a potential 3D object. So what you did is that you have got now a 3D object recovered from a point cloud. Amalgamation of point cloud to 3D surface modeling is the one that you did. So this is a potential, I would say, information label. So this way, you are able to form out any kind of structure in the image, in the sense point cloud, if you know how to process them. While we tried with some of these classical algorithms, for example, the 3D voxelization is some sort of adaptive clustering algorithms, and segmentation is some sort of a version of this, let us say, watershed and region growing based kind of segmentations, which are classical approaches. And then we tried to find out 3D reconstruction algorithms. So once that are done, we try to apply the very same kind of approach to a different problem. Of course, the classification is something that we did with SVM kind of classifiers, which is again the traditional, let's say, learning-based algorithms. And once we got to know finding out a pipeline, then we tried on the same kind of 3D modeling for a quite different kind of application, that is crop 3D modeling. For example, if I like to model agriculture crops as 3 models, perhaps, so that I can actually find out 3D crop features, for example, height of a plant, or the width of a plant, or the area of something, I can easily find out if I have a true 3D modeling of the crops. So we try to have that kind of approach in extended to this crop application, where 3D point cloud model was used to differentiate crops and some estimation of some features, some properties of crops, using a kind of approach that you call a completely 3D model. So this is the kind of crop that we are trying to set up. For that, as I mentioned, we acquired point cloud. This laser scanning was also done in same field. In fact, multiple locations were used so that we'll have the geometry of so many points acquired in the same field. So that way, we have got so many scans. So obviously, the first thing that comes is that all these scans are independent scans. So you need to co-register them. So automatic co-registration of the point cloud itself is a very challenging task. Though we tried with the existing algorithms, but because our approach, our problem is not to worry on the algorithms of registration, rather, analysis. So we use some of these existing auto registration algorithms to fuse all these some 10 to 15 scannings into a final model which is now a combination of all these individual scans into a 3D model of the field. So if you have this 3D model of the field, and if you are having this kind of 3D models at different periods of time, then what happens is that you have got now potentially information which refers to the plant growth at different periods of time. So geometrical information of plants in true 3D metric at different periods of time. So that way you are able to find it out by simple statistical approaches. What could be the growth of crops between 2 dates, or what is the status of a plant at a particular area in the field. So all these kind of things can be answered if you have got this multi-temporal point 3D modeling. So which we did with the same thing. And finally, if you just have an example of that thing, this is the kind of plant that you can see. For example, sorry. So something like individual plants are now differentiated. So from this, you can estimate any kind of property, be it nitrogen or height or its type. So all those things are now potentially derivable from this 3D modeling. And of course, we use so many types of models, and which include different kinds of traditional approaches for segmentation, then a lot of filtering, then statistical models for estimation of these parameters, and then finally support vector regression based models for estimating these plant parameters. And this is a usual process pipeline that we followed, where individual plants are identified from the data. So you'll be knowing what's the top of your plant. So from that, you can estimate all the plant properties. And then when we actually validated with the ground data, for example, estimated height versus true height for different crops, as you can see, the error is order of some 2-3 centimeters between the estimated and predicted. Sorry, measured and predicted. And the correlation is 99% nearly. So the lowest is, for example, about 95%, and the highest is 99%. So you find that if you are able to precisely 3D model a crop, then the kind of measurements that you can make are very precise, which included different times of the prediction. So a lot of predictions are there. And based on those kind of properties, we have actually estimated the yield. What could be the potential yield of a plant? So measured versus predicted. So even that also you can see that the correlation is very, very straightforward and more than 90%. So that way you will be finding out that a crop 3D modeling using remote sensing data, precise point cloud remote sensing data, would be much more amenable for a farmer to look at the growth or status of nitrogen at individual plant level. So these are all different properties that we made as a function of different growth stage as well as nitrogen levels. So then, while this is the application that we extended this point cloud remote sensing to estimation of the crop parameter, we also try to identify exclusively using this LiDAR point cloud differentiation of the crops, in the sense classification of the crops based on only point cloud. For that, we use while these are all statistical approaches or even traditional SVM based kind of prediction algorithms that we use to model, we have gone for this estimation, for example, this what I would say identification and classification. We have gone to the traditional way of looking at this deep learning methodology. So some of these recent architectures have been adapted and modified to suit to the data ingestion of this remote sensing kind of point cloud. And finally, point clouds are classified using this kind of deep learning methods for plant level 3D modeling. So plant level 3D identification. So you will have a crop map which will be labeled for plant at individual plant level, and the perspective is 3D. So this is a typical methodological process flow that we followed, and where some of the things are usually including statistical filterings and then learning based point cloud models. So if you look at some of the accuracy metrics, this is the thing. And the model that we followed was a kind of, recently there was a model which called PointNet. So we adapted that model and updated with an architecture such that we are able to ingest this LiDAR point cloud. So traditional algorithm of the point node is very limited. It can take data only from, for example, this Kinect kinds of indoor sensors. But our LiDAR point cloud is some sort of 3D point cloud pertaining to crops, and a few millions of points are there. So the network has to be optimized to ingest and process, which we did. And finally, classification was done at the individual object level. So finally, if you see this, now these are the kind of point cloud classification using different kind of crops as well as its in basic infrastructure, which included the background. And we also compared with one of these graph-based kind of, again, there are traditional approaches. One is a point cloud kind of thing, otherwise, differential graph-based kind of convolution neural networks also. So we just implemented for its comparison and find it out how the particular point net architecture that we adapted works for this crop classification. And if you see a 3D perspective, it looks something like this. So this is the crop identification done at individual plant level. So once you have got this identification done, then you can estimate points, let's say properties of a crop or at the plant level. So all sort of parameters can be estimated from this particular output. So that is the kind of intention that we wanted. The accuracies are okay, not so great, but about 70%, 70 to 75%, we could able to notice in this kind of deep learning things. But we like to see how it works when you have got all together a different approach. And then the third application that we like to put is a kind of hybridization of traditional approach and this with machine learning or let's say deep learning approach for water quality mapping. Let us say here the mapping parameters are something like functional water quality parameter. For example, we need to find it out functional relevant in the sense whether the water is potable or something like, let's say, drinkable water or not. So if you are able to answer such kind of concern, then the kind of water quality that you call is a very functional water quality. So based on its water quality, you should be able to judge whether the water is really good quality for human consumption or it is only good for some sort of industrial use. So with that perspective, we try to find out an application which is a mixture of traditional algorithms as well as deep learning algorithms. The problem is that it is not easy to identify or estimate water quality, because when you like to have this water quality estimated, you are actually estimating a host of parameters which quantify the quality of water. That means this water quality itself is an amalgamation of estimations of different parameters or parameter related to water. So if you're able to find it out methods to estimate those kind of parameters, then based on the ranges of those parameters, you are able to decide upon whether the water is good quality or something concerned. So this is one evolving area where this remote sensing is increasingly sought for measurement of lakes, let's say rivers, other reservoirs, and even small tanks and other kind of things for very finer quality estimation of water. So we tested initially this with one airborne hyperspectral data, which we acquired here in Kerala itself. 1 second. So this is again a hyperspectral imagery acquired at 4 meter using a airborne platform. and on a actual backwater lake in Kerala that we call Vembanadu. On the same day, we actually acquired several ground measurements. Ground measure nothing but water samples. So spreading across the lake on a linear direction, we acquired so many water samples and tried to have the laboratory testing done. So that means we know the quality of parameters at some discrete locations. Now, if we estimate the parameters from this remote imagery, then we should be able to compare how closer are these estimated parameters to the measured parameters. So that way we acquired water samples as well as spectral data even from the water. This is an instrument which actually acquires with hyperspectral images as we move on the ground. So airborne as well as ground-based hyperspectral images were also acquired so that we'll have a spectral data at two levels and then relate the measurements from different things. Now, I am sure you would have heard the major limitations of this machine learning, particularly the deep learning kind of thing. Deep learning things are good if you satisfy the basic data training needs. If you have access to thousands of labeled examples, which are representative of the problem that you like to solve, then those approaches are very good in generalizing the capability. On the other hand, if you have got a very low number of your training examples, then deep learnings are actually destroyed. They won't be able to learn at all, and whatever the things that you expect from them, it will be nothing. So they won't be useful at all. That way, traditional approaches, statistical or even statistical learning algorithms are much superior in performing when your training data or your label examples are a few. Obviously, you would have seen that in most of these deep learning architecture based kind of thing, the number of examples required for you to import any kind of training is that number is always in thousands, not hundreds. So it could be 5,000, 10,000, 20,000, such kind of examples are usually given. And by looking into those kind of iterations only, an architecture learns something. Then it has the generalization and it predicts. But in this kind of water quality related kind of thing, you cannot have thousands of samples acquired. So you are not luxurious to acquire a few thousands of laboratory measurements every time. So it is prohibitively cost, or it is not possible practically. Even having 100 measurements is a big thing. So we acquired about 100, which itself are considered to be a big number. So now our question is, using these very few, in the sense by the terminology is deep learning, these 100 is a few, nothing. But we like to see that this deep learning architecture is tested for water quality with the basic assumption that you have access to very few training examples, and then you need to make the networking function for you. So for that, what we have tried out is the kind of an intermediate approach, wherein without directly going to train the deep learning architecture, we have not innovated on the kind of architecture, but the innovation is not based on the deep learning architecture. That is not a big problem. In fact, the problem is that how would you satisfy the basic requirements of data and reference examples for any typical network architecture to learn? So that is the biggest problem. If that is done, then 90% of algorithms and 95% architecture perform almost similar. So you won't find a sea change in the performance of any problem just by changing the kind of CNN to RNN or RNN to Latin or RNN to GAN. Those things are not that much really, I would say, play. The play comes here in actually in the training data and example how you make them. So what we did is that how to make these 100 examples into few thousands was the biggest problem. So for that, we actually have adapted the traditional algorithm. The genetic algorithm is one of the very widely used, evolutionary computing algorithm. If we know employing this algorithm to this problem or not is the question. So what we tried is that we employed this genetic algorithm to
improve our training rate. In the sense, we should have now, instead of 100 pixel, 100 laboratory example means 100 pixels. So it won't be sufficient. So we need to have an example of, let's say, some 2000 or 3000 at least. Then how to get those thousands from few is the biggest problem. So if you know how this genetic algorithm works, there is a way which actually does this kind of function. So for that, based on the kind of original data, we have taken 70 out of them, 30 we kept for validation. Then we defined this primary CDMA and neighborhood of, let us say, some 8 by 8. And then based on this neighborhood, you are going to predict out the potential examples of pixels within this neighborhood. So genetic algorithm is now improved, improved to generate a lot of permutation combination and testing the potential of neighborhood pixels, which could be the candidates for the pixel which is akin to the kind of training pixel. So first iteration is done, and then you will be selecting based on the best fit criterion, and then you get a certain number of pixels. Then use that additional new set of pixels to again propagate. So again, those are considered as seed population, again with the second level of patches, and then try to figure out the pixels which are very closer to this kind of first line of pixels. So you get additionally some more number of pixels. So in the second iteration, perhaps we would have got some 500 pixels based on the all the permutations and combinations and kind of mutation that we import randomly in the genetic algorithm. So you get a new population. That means we would have got now by 500 examples. So that means 100 now become 500. Now make this 500 into next round of reaching to 1000 by again after changing the alterations of your genetic algorithm and fitting the criterion function. And that way, if you like to entirely do that thing, ultimately there will be a point where you are going to have at certain iteration hundreds of points, or not hundreds, maybe a few thousands of points, which are potentially equal to the let us say original ground truth points. So that pixels are now thousands, which are equal to a kind of quality which you call them same as labeled point. So that way, those all will be candidates for you to train the algorithm. So once we got those kind of iterations, then what we did is that we identified a kind of traditional, let's say a simple generic algorithm of this deep learning, which is nothing but RNN, and then we try to give the different images as input. So you will find all these kind of architectures, and then finally finding out estimations. So these are all routine things where optimizers as well as architectures are done, and loss function also typically a statistical error based thing. And finally, this is compared with the traditional accuracy of 30%. So the output now is now predicted with the sense whatever we predicted is now compared with the measurement that we have with the original 30%. And as you can see that the quality is about, initially it will be about 30%. And the accuracy varies by parameter. For example, if it is, let's say, chlorophyll, then the accuracy could be even 70%. If that is, let's say, dissolved organic matter, then that is 50%. If the parameter is something like, let's say, biologically demanding oxygen, then accuracy is actually 75%. So you get these kind of parameters which are quite different in their resolution as well as their interaction spectrally, and the ability of this networking based or this any kind of learning based deep learning architecture to map the cause and effect relation. Sometimes the predictions are one way. You would not be knowing that what caused this kind of prediction. So there won't be a kind of cause and effect relationship. Sometimes these deep learning architectures also behave the same way. They will tell you answer, but if you ask how this is, then there is no answer from them. So that kind of problems are there with this thing. But yet this is an attempt to find it out some of the parameters which are successful and some of the parameters which are very vague. So that way we would say that partially there is success of water quality estimation with this kind of approach. But we need to continue building upon this success, and maybe we need to find out, involvement of any additional parameters, perhaps a better candidates for this kind of architecture. That is yet to be seen. And these are all just simple plots which would be showing the measured versus estimated, the kind of outcomes. And then, interestingly, when we use the same kind of example data, original example data, and use the traditional machine learning algorithms, for example, random forest or XG boosting or these kind of approaches, then actually the quality of prediction is much higher. So that is one observation that we made it out. Though we tried to cheat the deep learning architecture by saying that you have got now 3,000 references, though in originality it is very few, it could able to perform at least some 50 to 60%, but we know that 56% is inferior. When we compare that with the same thing that you retrieved from this traditional machine learning algorithms, now results are actually much superior. As you can see, the lowest is that 80% is the accuracy. So that way, it shows that we need not to be simply saying that everything that is deep learning will be good. So it is a case and it better candidates, and they perform much better, maybe with very less complexity as well. So that we actually have demonstrated that way. And while we could able to find out only 3 parameters which are potentially retrievable from deep learning, okay, with the kind of generic algorithm equivalent, only 3 parameters with some level of accuracy. With that traditional algorithms, we could able to find out altogether 7 algorithms, 7 parameters estimated with more than 80% accuracy. So that is one thing that we need to keep in mind. So there is still a market for the traditional machine algorithms. Okay, so we'll not be feeling bad that this entire deep learning is evolved and we are not catching it up. Not necessary. Sometimes being shallow also much help. So we find it out like thing. Sorry, this repeated. And then the fourth application that I like to also share with you is that it is a kind of intended detection. As I mentioned, I have one spectrum which I know who is that material. Now my aim is to find out that particular material in the imagery. So if my material contains hardly some, let's say 4 or 5 pixels, that means my imagery should be, output image should be such that entire thing should be background, in the sense dark, except the locations where this target is there. Okay, so that is expect that I like to get the thing. As detectors, we applied several of these traditional pattern recognition algorithms, which are statistical and a little more subspace kind of probability-based detectors. So we have not, we did 2 experiments, first with traditional pattern recognition algorithms, and second case with these deep learning algorithm. So the first thing that we like to share is the traditional thing. And an experiment is something like this. We have got at specific locations some sort of material that we spread whose spectra are known to us. Now, based on these very few spectral examples, we should be finding out in images where they are located. So that is the question. And of course, it is a very complex process where you need to do a lot of processing of this imagery, and then a lot of distortion to be removed, which include atmosphere as well as other surfacial interferences. And finally, you are going to have this imagery, and that is the case for detection. This experiment actually we did at 3 different platforms. At the ground level we have done, and at the airborne level, so airborne hyperscopic imagery, ground-based imagery, and satellite-based imagery as well. So the very same targets are now actually identified based on the ground and in the air and in the space. So it is a complex process. Now, if you see this, for example, this is airborne hyperspectral imagery. Now, if you see some of the targets which are located, there are very few discrete instances. For example, some 4 or 5 instances of it. Now, you need to find it out that particular locations in this entire imagery. So, if you see the kind of ground truth, then these are the only pixels that you need to map it out. Now, if you see how they look like in the ground truth, these are the little more elaboration of the same pixels. So, you have got hardly 5 pixels as the candidate pixels. So, you need to find it out. These 5 pixels among a mix of, let's say, 1 million pixels in the imagery. So, this is the process that we use. Let us say a lot of corrections and a lot of algorithms, something kind of thing. And then finally, based on the kind of pattern recognition detection algorithms, we got the result. So if you like to give you a glimpse of the result, it is something like this. For example, now we like to detect the targets in the airborne and satellite imagery. For example, now my data that I am looking out for, my reference is actually from the ground. I have got spectral signature only from ground. So based on my signature, I should be looking out in the airborne and the satellite based on the ground based knowledge. So ground spectra are now searched out in the airborne as well as satellite images. So this is the result from airborne and this is the result for satellite. As you can see, this is the target. The grid is the true target. Okay. Here also you can see that the dark one is the true target and the bright pixels are actually the target which are identified by the algorithms. Now as you can see, some are very precisely identified, as you can see, which are very precisely identified. Some of them are identified, some type of targets identified, but you would also find some false positives as well. So you would find that the case of detection is there, but you also find that some false positives are there. And when you upscale the detection to satellite, then you will find that sometimes even the target is completely missed out also. So you would be finding out that the pixels which are going to be identifying are being identified, and that identification is a function of different algorithms. Now, as you can see, if I find it out, what is the target detection ability as a function of algorithms, then that actually changes. You can see that different algorithms perform differently. As you can see here, in this algorithm, when the target is seen in the satellite, you find that the detection is a little bit ambiguous. So background also looking something like very potential target like thing. That means this is something like a kind of a confused state of target detection. Whereas here, if you see one algorithm very distinctly performed, no background at all. Here you have got some level of enhanced background, even though targets are detected. So here if you see, when you have got satellite and the base reference is airborne, then two algorithms seem to be better identified and some algorithms seems to be completely random. So detection is there, but we cannot generalize saying that everything can be detected using this kind of hyperspectral data, but a function of algorithm as well. Now, these are all different ROC curves which differentiate how quality are the identification. So probability of detection is plotted against the potentially all these false alarms. Now you can see different cases of algorithms. Some of them are very precise, some of them are sheer random. So you will find that also function of background as well. Okay. So in principle, what happens is that neighbors matter a lot. Whenever you call target detection in any imagery, the major problem that is causing either your detection is failing or detection is little bit ambiguous, but it's successful, is controlled by your neighbor actually. So you need to mind your neighbor. It's always important to keep it. Okay. So in our life as well as in your imagery also, you need to take care of neighbors. So if you are able to model the behavior of neighbors And if you know how to avoid their interference, then the target detection can be very successful. As you can see the performance of different targets and as a rate of false alarms. Okay, so that is one important thing. So the algorithmic intervention that is required is a combination of these three things. For example, a combination of background, how distinctly you differentiate background from the foreground. And that includes sophistication of your detection algorithm. And in that way, it is not necessary that only the spectra do everything. No, spectra does for 35%, maximum 35%. The remaining 2/3 are mainly by the geometry, that is the type of object, and the neighbor. So, if you like to have any target detection system developed and you are looking out for very successful detection, then you need to find out, you need to study the interference of ground versus target as a function of background contrast. And you need to find out the algorithms which will be sufficiently suitable for different sensors, okay, as a function of their complexity. If the algorithm is very complex, then it is a big problem. It should not be that much complex, because if an algorithm is complex, then its repeatability is going to be the question. So you cannot find it usage across different domains. So it's a matter. On the other hand, if I say that I can have my data in thousands of bands, if too much is there, then it is a big problem. Again, you're going to be redundant and data itself is going to be a problem for you. So you need to have a balance between the dimension of data, algorithm complexity, as well as finding out contrasting approaches between background and target. So if you follow this kind of interventions, which will be a mixture of algorithms, computation approaches, and a kind of logical expression, then you will able to find it out targeted detection of materials in hyperspectrophotometry with a realistic mode. I think that's what I think. As we try to do one experiment, we just try to have one object dropped on the surface whose spectra is known to us, and if a drone flies by, then we should be able to locate where this particular object is dropped simply by analyzing this drone based thing. So that is one more experiment that we did. So this is the experiment setup as we designed, and this is the imagery setup where this is a metal sheet, very thick metal sheet of about 1 meter, and this is open here. This is partially obscured. It is obscured a lot. So if we fly drone over this area, then we just like to find it out the existence simply by automation of the algorithm. So that is the approach that we tried. This is one of the images that looks like different cases. And if we try to find it out, the detection based on the drone, then you can see these are the statistics of the detection, or you can say algorithm. So the red color is actually the full the ground truth. Okay, the blue lines are the target detected. You would find that completely visible, you would able to find it out. So partially visible in some cases is closer to the target but not actually hitting the target. So you would find that you are able to identify the immediate neighborhood of the target as a target, and target is actually missed. In the case of obscure, which we could not able to find it out, there is some sort of target detected. So which is showing some sort of target detection even as a case of automation that you like to do. And a further extension of the kind of trial and error, or I would say logical modifications of the deep learning approaches for target detection, we try to have some more tweakings on the target detection architectures for establishing the efficacy or understanding the capability of these evolving approaches for target detection. So what we did was we tried out to have this target detection done on these hyperscale images. And the problem is that we have only actually 5 pixels now. Only 5 targets are there. That means the number of examples that now we have is only 5. So based on the 5 examples, you need to train the algorithm. So that is the biggest problem of this deep learning. So how we approach it is that instead of trying to find it out, let's say partially performing the genetic algorithm, we try to look from this intervention based thing. So atmosphere is one thing which is a very dynamic. So it can introduce different kinds of dynamics in your data. So what we did is that we generated a lot of examples of this training data, potentially training data, by altering this atmospheric composition of this spectrum. So by simulation of the atmosphere potentially influence of atmosphere and different scenarios, we have actually generated points which are actually 30,000. So that is the capability if you know how to deal with the different spheres of remote sensing. So by very sophisticated atmospheric modeling and simulation, we generated 30,000 spectra from 5, only 5 spectra now become 30,000. Now we try to detect the images in the cell targets in the imagery. Now as you can see, and that we try to compare with the traditional thing. This is the first one is the traditional algorithms. Now you actually can see that the detections are much more reasonable, if not completely 100%, but the detections are actually reasonable. As you can see, the identification of only few pixels with the traditional algorithms. And when we use this, of course, different algorithm, as you can see, different targets have different kind of behavior. So obviously is a function of the nature of target as well. Okay. And some are very good, some of them are not so good. So function of algorithm, function of the target as well. And as you can see, some target looks like the entire background is target. So it's very bad, any kind of thing. And if we go with this machine learning kind of things, as we proposed a dual deep learning architecture, wherein data are subsetted in some manner and given architecture input for 2 different types of things and processed separately and finally combined with some kind of criterion, then the results are much more logical. So you find that targets are now detected with little more precision. So there is some sort of detection rate achieved. So that way, we still can find that there is a way out if if we like to approach target detection from a machine learning or advanced deep learning architecture. The challenge is maintaining the kind of architecture learning, and when you're looking out for only few pixels. So mining out information which is really very damaging or you can say demanding from example of one or none is the biggest challenge. So that's why the information retrieval from the targeted information in remote sensing imagery, combination of approaches that you like to condition the signal, that you like to simulate the signal in different conditions, and tweak the architecture such that the architectures are amenable for enhanced signal representation. So if you are able to do that, then perhaps you are able to finding out a way of targeted detection using any kind of remote sensing imagery. And before I close, another thing which I like to share with you that finally actually we ended up here. It is the point where we ended up in waste. So the waste is the biggest problem for us. Okay. Now the entire world is running after our run down by this waste. So now we thought of identifying, let us say, some sort of material targets which are invisible. For example, if you like to find out the presence of some sort of plastic residuals in sand. It can be sand, it can be soil also, it can be water, it can be anything. Okay. So if you say from environmental perspective, if you like to quantify the quality of environment, spatial environment for its pristine composition, and like to see what is the potential impact of all these plastics and their degradation on the quality of environment, then finding out the composition of microplastic, which are very, very small plastic particles, order of nanometers or micrometers, in this kind of environment is an important thing. So using such kind of remote sensing approaches, can we able to quantify the composition of this kind of ecological settings is one of the things that we started off. And for that, we just tried with some sort of data collection, which included the typical material that would be ending up in the environments, and trying to acquire hyperspeckle images of very same images, and trying to find out their speckle signatures, how do they behave. So for that, what we did is that we did several experiments where we dump different proportions of plastic residuals, some plastic powders, plastic pots, which are different thing, on different sorts of the soils and sand, acquired images over the same area, and trying to process and apply the kind of algorithms which would be perhaps figuring out the proportion of these materials in the environment. So if this is successful, then there is a lot of vibrancy in that. That makes us to have a very sophisticated system where we like to have this real-time quality of environmental compliance and environmental parameters, which would be very vital for the present context, where you like to estimate remote sensing based quantification of environmental quality, which included water bodies, beaches, riverbeds, even in fact agricultural fields as well. Nowadays they are also being suffered with a lot of the plastic. So that is one application that we just started. So we are still in the initial stage of our efforts. And that's what I think I wanted to share with you. And I am also keen. In fact, we have extensive work from our team, where we like to invite the people who are interested in doing some of these typical image processing intensive or information mining intensive works for academic interest. So it can be, let us say, something which you like to do, and we also like to be happy to share with our resources, and where we can set up experiments, or if you can have some sort of experiment like to do, then we can set up that kind of thing, because we have extensive infrastructure. We have got a lot of imaging systems which are very high quality image systems, so much of sophisticated software and data access to host of ISRO and other foreign space agencies. So that way we have a very well stocked laboratory of remote sensing that helps many people to do many things, both data algorithms and instruments. So which we like to offer to the people of interest. So if you are willing to do, if something interesting to you, we will be happy to help in that way. And thank you. That's what I thought.
Madam, queries, please.
Dear participants, you can unmute yourself and you can ask your queries.
Madam, your voice is not audible.
Okay.
Hello. Hello.
Yes, sir.
Madam,
Yes, sir.
speak loudly.
Okay. Participants, you can ask your queries now.
Sir, before that, I want to ask you whether, I don't know whether I ask you or not, but I have a doubt. I have followed all the entire session of your.
It has no limit. Answers only have limit.
Sir.
Yeah, please.
Sir, present, what are the challenges are there as you are working as an industry person, you know very well. Some challenges are there as we explained on advanced target and remote sensing. So can you throw out what are the major challenges are there now for target detection?
One, as I explained, the target definition itself is a question.
Yes.
In the literature, you may find in the people solving or giving some kind of papers where the targets are portrayed as entire urban. For example, in a city, they say that entire urban built up itself is some sort of target. But you know, in the city, other than buildings, what you can expect? So that cannot be targets. So target should be few. So what happens is that the first thing that comes is the realizing the fact that targets are limited in their spatial distribution. So you will be finding that targets are very small, objects distributed in an image. So that makes them to be having only very few pixels. So when you have very few pixels of potential target object in imagery, then how we are going to get a training data for that?
Okay.
How would you first give a sort of reference data when you have very few pixels? If there are, let us say, 10 pixels in your data, if your algorithm requires 1,000, then how we are going to have this problem solved?
Yeah.
That is the first thing. And the second thing is that target is a function of its spatial size. For example, you have acquired image at 10 meter, okay, or the satellite image that you are using would have been, let us say, at a 10 meter resolution, whereas the target that you are looking out for would have been spatial extent of here much lesser, let's say 2 meter. Okay, then what happens is that now your target is not actually even a full pixel.
Yes, sir.
It's a very small subpixel, a fraction of it. So under this condition, how you are going to map something whose spatial distribution is not even perceived by a pixel? That is another thing. And the third thing, most important thing is that how would you avoid human intervention in this thing to the much extent possible?
Human intervention is a very important task, sir.
Yeah. So, and another thing is that most important thing perhaps from your even ECE background, some of the, some technical things are very common to ECE, wherein the process to happen real time. We cannot wait for hours and days.
Yes, sir.
If you like to have this imaging analysis done on the go, let us say every second, then some of these approaches, in the sense some hardware related image processing, remote sensing image processing done on the chip, a small board or the chip, okay?
Yes.
And then in the sense we should not be using computer kind of thing, but it should be a small chip or on board. So the processing should be happening on the board and the results should be displayable. So it is something like, I would say, real-time image processing. Yes. So if you look at these 3 to 4 kind of challenges, they have multiple applications and they will be there in every application.
Yes, sir. Yes. Yes, sir. Thank you, sir.
Thank you.
Any queries still?
Madam, anything is there?
No, sir.
Yes, madam. So, sir, I want to read out. I have learned what main focused points I want to read out actually from your lesson, from your session. First, we have started with precision crop mapping for hyperspectral imagery and terrestrial lidar point cloud and water quality estimation and target detection, like experimentally plot of GKVK Bangalore and crop mapping, and DL targeted automatic crop identification, leader point cloud, 3D reconstruction, 3D leader point cloud, and measured and estimated biomass across the growing seasons and temporal prediction levels. Latest model is crop pointing net and water quality mapping, which is types of water quality methods are there, and genetic algorithm, target detection using hyperspectral imagery, like deep learning, like that. I think I have learned the another thing is genetic algorithm. They have studied genetic algorithm only on image, sir, but you are showing the various real-time targets, how to detect it, and how to initialize how to select the population, how to do the mutation, how to do the fitness and the crossover. It's an excellent session. I enjoyed a lot actually. So I hope the participants are also enjoyed a lot. You are explained elaborately, sir. We have such type of great personalities we have discussed today. I have learned 3 new points also in target detection practically. I think these things are very useful to the as a faculty. These things we need to express in front of the students, because the ultimate goal is the student has to get the benefited, society has to get the benefited ultimately. That is the main motto of the Atal, and like you personalities, big personalities, and like our institute, we are all those things are doing for the benefit of the society.
Yeah.
So I would like to thank from the participants and from my side, from my bottom of heart. So I would like to thank you so much.
Thank you very much, sir. Thank you very much. It's nice meeting.
You are given elaborately explained
for your remaining days.
Once again, thank you, sir.
Thank you. Thank you.
Sir, one thing request from my side.
Yes, sir.
Please, I need your whenever we request you, please make your convenient and please come forward, sir. You are helping to the society. Please, sir. And also, we need some cooperation from you in future also. I will be in touch with you, sir. Please, sir.
Sure, we'll be happy to to interact and continue. And in fact, if you have some sort of works which are related, and definitely anything that you call, we'll be happy to engage in that.
Sure, sir. Sure, sir. Thank you, sir. Thank you so much, sir.
Even some of your faculty colleagues, or even from other department as well.
Sir.
Will be nice.
Sure, sir. Thank you, sir. Madam, please.
Thank you. Thank you, all of us. Bye, sir.
Thank you, sir. Thank you once again. And thank you all the participants. Next session will start at 2:30 p.m. sharp. Please join 5 minutes before the start of the session. Thank you all.